So good morning. Next presentation will be taken by Martinoia, and we regard the re-engineering process of a device for testing and calibration of an inertial platform. So please, Marco, the floor is yours.
Thank you. Hi, everyone. I would like to introduce to you the project that I followed during my internship at Marelli Motorsport as an area, which involved the re-engineering process of a device for testing and calibration of inertial platforms. Among all the products made by Marelli, the one on which I focused on was the IPS. The IPS is an inertial platform with 3 accelerometers and 3 gyroscopes, mounted on motorbikes used for MotoGP, Moto3, and Moto2 championships. This device basically measures the linear and the rotational accelerations felt by the motorbike during a lap and send this data to the ECU. In order to work properly, this device has to be calibrated. To do so, it is mounted on a gimbal, which is basically a mechanical arm, which imposes some predefined rotation and acceleration to the gimbal, to the IPS. Then the measurement acquired by the IPS are compared with the one acquired by some precisely calibrated sensor mounted in the motors of the gimbal. So a mathematical correction can be applied to the first one in order to make them match the latter. In order to take into account also the thermal deviation that can occur because the IPS is mounted very near to the internal combustion engine of the motorbike, the whole process takes place into a climatic test cell, which basically take the whole system from 0 to 80 degrees while all the whole calibration is performed. The problem is that the test cell vibrates, and these vibrations are captured by the gimbal and enhanced by the structure, the mechanical structure. Therefore, both the measurement acquired by the IPS and the sensor in the gimbal are ruined by the noise coming from generated by these vibrations. So we decided to modify the gimbal in order to overcome this problem. The roadmap of the project was this one. We started from the starting point, the bad IPS calibration, and we decided to measure the excitations given by the climatic test cell and the response of the gimbal. Comparing the two, we proven the vibration involvement into the problem, which had to be proven. And from the measurement of the gimbal, from the measurement of the response of the gimbal, we understand how to model, basically, to generate a mathematical model to simulate the vibrational behavior of the gimbal. So we actually simulated the behavior of the gimbal, and this allows us to know how to model all the mechanical connections between the parts, the mechanical parts of the gimbal. This was important because this knowledge allows us to actually simulate the modified model of the gimbal in order to know a priori what would have been the behavior of the new product. Then we actually produced the gimbal and evaluated its performances, and then it was necessary to design a vibration isolator to add to the whole system, and then we evaluate all the performances, the final performances. So first of all, as I said, we started measuring the excitation given by the climatic test cell. In order to do so, we used 3 integrated circuit piezoelectric accelerometers from Dytran, mounted as it can be seen in the photo, simply attached with bicomponent glue. But the first measurements that we take were ruined by the noise coming from the electric power grid, which was captured by the accelerometers. Therefore, we decided to wrap them in electrical tape in order to shield them from the noise. The result is this one. As it can be seen, the noise coming from the power grid is still present, even if highly reduced compared to the first measurement performed. But the important part is this one, between 100 and 500 Hertz, there is a concerning frequency range in which the acceleration are high, the excitation are high. Then we move on by measuring the natural frequencies of the gimbal. In order to do so, we bolted it onto the shaker plate and gave him a sweep sign profile at 1 GN in order to measure its natural frequencies. In order to do so, we mounted also 4 accelerometers to use as control loop for the control loop of the shaker, and 2 for measurement pickups. The measurements were this one. The interesting curve is the red one, which is the one obtained from the accelerometer mounted on the plate. As it can be seen, between 100 and 400 Hertz, the response of the gimbal is very high. This proven that actually the acceleration took part into the problem of the bad calibration of the IPS. In fact, comparing the response with the excitation profiles, we can be seen that the high part of the response is overlapped to the high excitations given by the climatic test cell. Then we move on, generating a CAD model of the gimbal and simulate it using SimCenter 3D. For the mesh, we use the C-Tetra 4 components and allow the program the software to automatically change the dimension of the mesh, of the elements of the mesh, in order to have a simulation which was both fast and precise. As I said, the important knowledge coming from this from all this process of simulation was how to model the mechanical connections between all the parts. As it can be seen, we decided to utilize some RB2 connections between the various mechanical components, which were iteratively modified in order to make the simulated results match the measured one. So this is the connection for the vertical arm, and this the one for the horizontal arm and the blade. And we also modeled the bolted connection with the shaker, simply imposing zero displacement to the two holes highlighted in the slide. These are the result acquired, but the most interesting part is that actually the simulation was able to simulate the behavior, the real behavior of the structure quite well. As can be seen, the error is well below the 10% threshold. Thus, we decided to model a new configuration of the gimbal. Basically, we decided to make the whole structure more stable. In order to do so, we modified the feet, and we removed the motor in the base of the gimbal, which was useless, and introduced some backlashes. Thus, the only mechanical connection which we didn't model before was the one between the vertical arm and the base, which was decided to be modeled with some RB2 in order to resemble the very stiff connection between the two parts. The results obtained are this one, and comparing the natural frequencies obtained with the excitation profiles, we can say that the first 3 modes are not cause of concern. I want to remember to you that the first 2 peaks at 50 and 100 Hertz are the one coming from the noise of the power grid, and the 4th and 5th node are overlapped to the high peak of the excitations, while the last 3 natural frequencies are not as cause of concern and the 4th and 5th nodes, but have to be taken into account. So we actually made the mechanical modifications and decided to study the behavior of the gimbal with the same exact process that we utilized for the baseline model. thus bolting the gimbal on the shaker and utilizing 4 accelerometers in the same places. The results are this one. And comparing the simulated and the real natural frequencies, we can see that actually the simulation did a good job in order to simulate the actual behavior of the gimbal. So all the things said before, all the consideration made before on the various natural frequencies holds true. This means that it was also useful, necessary, to dimensioning a vibration isolator for the gimbal. In order to do so, we utilized the formula, the procedure listed in the Angst-Pfister catalog. We selected the excitation frequency that had to be reduced, the efficiency of the isolator, and from the second formula, which is the formula for the natural frequency of a simple plate, a vibration isolator plate, we were able to decide the material and the geometry of the isolator. We decided to utilize the simple plate of 500 by 300 by 30 millimeters made by Silomer 11, and after we performed the controls on the static deflection, which has to be less than 20% of the original height of the plate, we proceed with the evaluation of the improvements. As it can be seen in the range between 100 and 500 Hertz, the concerning part, as I said before, there has been a reduction of about 84% of the excitation perceived by the IPS. Therefore, we were able to obtain a system which is both more compact, as I said before, and allowed us to perform the calibration in also a smaller climatic test cell, and a system which is actually able to perform a quite good calibration, which doesn't take into account the problem coming from the excitations given by the climatic test cell. I would like to thank you, and if there are any questions.
Yeah, okay. Thank you, Marco, for your interesting presentation. Yes, I have a small question that actually regard the estimation, the measurement of the natural frequency by means of the shaker.
Mm-hmm.
In your test, actually, you have used a monoaxial shaker. So the excitation is monoaxial, so you just in the vertical direction. So my question is, are you sure that all the modes that also have a mode shape quite different from that you have obtained can be excited by a simple monoaxial excitation, and maybe was not necessary to excite also in the other direction, orthogonal to the vertical axis?
Okay, so we decided to excitate only on the vertical axis because we measured that actually the accelerometers used for the I can say to measure the excitation given by the climatic test cell. Two of them, the smaller one, are only monoaxial. The first one near the scene, near the viewer, is a 3-axis accelerometers, and during these measurements, we understood that actually the orthogonal accelerations were not cause of concern. The biggest one were only on the z-axis, the orthogonal one, compared to the base plate of the oven.
Okay, thank you.
You're welcome.